today. One is, I want to show you a little bit. So if I have some complex number s, we can, and this is something we've done. We said you can write it as the modulus times e I to some angle theta. That's something that we've been doing. And if I have another number, like capital S, it has some modulus, capital R, E, I, I'm just giving you some numbers.
That's beta, B, right?
Yes, beta. So you can, if I wanted to define S times capital S, it's really as simple as what you would expect. It's R, lowercase r, times capital R, E to the I theta times E to the I phi. But that cleans up really nice. It cleans up really nice. How does it clean up? It cleans up as little lowercase r times capital R times e raised to the I parentheses theta plus phi. Okay, there's a lot of different things we can do here. Let's try this. If I take S and I multiply it by S, that would be R times E to the I, parentheses, this is theta plus theta. Is that what I want to do? Not exactly. No, don't write that. You probably already did. Let's try this. Not S. Let lowercase r be 1. Let lowercase r be find identities for double angle formulas. That's two angle formulas. So here we go. Let's say I take S times S. This is going to be E to the I theta times E to the I theta. And that's going to be E to the I times 2 theta. See how reasonable what I did there? Just taking S and multiplying it by itself. Let's try this. So on the left-hand side, I have the cosine of theta plus I times the sine of theta in parentheses. And then I have another one of those parentheses. I have the cosine theta plus I times the sine theta. And then on the right-hand side, let's rewrite it as the cosine of 2 theta plus I times the sine 2 theta. Okay, before we go on, this is not a trick question. This is a need your help question, because I have the worst time remembering these. I'm curious. Does anyone remember what if I gave you the cosine of 2? I don't know, whole theta. Does anyone remember what that double angle formula is? Okay, I'll answer it once.
Cosine squared of theta minus tan squared of theta.
Cosine, let's see, say that again, Marcel, cosine?
Cosine squared of theta minus sine squared of theta.
I like, is that a question or are you?
I'm interested in weighted, yeah, okay, that makes sense. I was thinking like weighted is equal to 1, no, that's only plus each other.
Yeah. What about sine of 2 theta? Does anyone remember that?
Sine of theta is cosine.
Say it with confidence.
2 sine of theta times cosine of theta.
There you go. Good. I think that's it. That one seems easier to remember. So I find both of those a little difficult. Let's see if we can get ourselves out of a bind. If you have to prove that with triangles, you have to be pretty creative. And I'm going to say, I always have to look those up. But let's see if we have a more, yes?
Could you explain the step where we went from cos I sine theta to the right side?
Yeah, I will. Good. I'm glad you asked. So this is this right-hand side. And all I did is apply Euler's identity to e to the I theta, that's this one, and to this one, e to the I theta to that one. And then on the right-hand side, so remember, Euler's identity really says that if you have ei to anything, it's that anything that becomes the argument of the trig functions. So over here, I regrouped it. I added theta and theta. So there's my anything. So on the right-hand side, I get the argument is now 2 theta. Over here, I left it as just a single theta. And so that's what I did. I was just expanding this, and I was expanding that. So let's go. This is my concern. I'm wondering if Marceline's cheat sheet is correct. You see, she needs to make any corrections. So on the left-hand side, if I multiply these out, I'm going to come up with a cosine squared of theta. Cosine squared theta. And then, let's see, a cosine times I sine is going to be plus I cosine theta sine theta. And then I'm going to distribute the sine, so I get plus I sine theta cosine theta. And then what do I get? Oh, then I have an I sine theta times an I sine theta. That's I squared. That's minus 1. So this is going to be minus a sine squared theta. And then I'm going to leave the right-hand side as it is, but I'll write it so we have it on this board. It's still the cosine. 2 theta plus I sine. That's theta. I'm going to make an annotate. Let's do this. Oh, wait a minute. This is a complex number now, isn't it? So let's separate this. Separate into real and imaginary components. So let's do that. Let's take advantage of the fact that we're in the complex field. So we're going to separate by real and imaginary. So let's see. So the right-hand side, right, I don't have anything to do. But on the left-hand side, let's see. I'm going to start with my real. I'm going to put a parenthesis here too. I have a cosine squared of theta. Okay, I cosine sine, that's imaginary, so we'll come back. I sine theta cosine theta, that's imaginary. And I have a minus sign. So minus sine squared theta, that's a real function. Oh, plus I parenthesis. Now, oh, look at this. Here's an I. If I factor my I out of these two middle terms, this is a cosine sine. This is a cosine sine. The order of the multiplication doesn't matter. This is 2 times sine theta cosine. Cosine 2 on the right-hand side, cosine 2 theta plus I sine There it is. We're done. You see that? By using Euler's formula, the properties of complex numbers, here's our first one. This piece is the identity for the cosine of 2 theta. And if you have a blue pen, the sine of 2 theta is 2 times sine theta cosine theta. And so, isn't that just the sweetest thing you've ever seen? I thought that was just so neat. There's a couple of those in your homework for this section, so you get to have some fun with that. All right. There's one last concept for today. I'll need an eraser for this. Sure.
What is all about numbers then?
Just adding 2 numbers.
Okay, so what's the S? What's the big S and what's the little S? What's the big S and what's the little S?
Those are just 2 complex numbers. That's all. You could have called them X's and Y's.
Okay.
That's all. Or Z, you could have called them Z's.
And R is just
The modulus. R is the modulus. So I'll review that here in a second.
the modulus is drawing a line from the value
From the origin.
of the complex one.
I'll draw one. How about this?
It's like people imaginary between that, because it's,
Right?
And why for the big F?
Just so they're different. Okay, let me draw one for you guys. Okay, hey, Marcel, what was your question?
like a, oh, I thought it was a rectangle, but it's imaginary, like,
Yeah, well, you have to be able to go back and forth at a moment's notice. So let's draw these. So if you have your complex picture, here's my real axis and an imaginary axis. So if I wanted to graph S, a little s, it's a point here. It has a unit of theta. It has a modulus of length r. That's what it would be. And it would be, so you could say that S is the A plus B. So if that was S, what would R be? Yeah. So then R here, so this would be B. This would be A. I guess we can write it. B. Here's A. And so if that's our picture, then R, lowercase r, is equal to the square root of A squared plus B squared. Oh, here we go. So I'll be clear. We're going to, I'm just going to give this a name. We're going to study, examine they're called the roots of unity. I'll try to explain where it comes from. If I give you a problem of S squared equals 1 equals minus 1. So let me rewrite that. Sorry, hang on. So if I give you the problem of S squared plus, same thing, plus 1 equals 0. Before you started solving that, and I know you know the answer, but that's not the point. Okay, s squared plus 1 has how many solutions? Has 2 solutions, right? So if we solve this, I would say that s is equal to plus or minus I. Now, wait a minute, you might say, you might be like, that's strange. Well, let's take a look at that. I'm going to look at this. Again, here's real. Here's imaginary. So I have, bless you, I have solutions then of I and also of minus I. 2 solutions. So let's try this. If let's say I have the problem of s squared equals, what do we say? -1. That was our problem, right? S squared equals -1. How would I write? So -1, this is equal to, -1 is over here. If I match these up. This is equal to E, or what's, oh, wait a minute. What's the modulus on -1? The length. How long is -1? It's 1, it's a positive time, right? Yeah, I know, it's kind of tricky, huh? So, we'll graph that. Here's -1. And it has a modulus of just 1 unit. Okay? So if I was to write -1 in polar form, I would write it as 1, there's this r value, e to the I times pi. Does everyone agree with that? Did I do that right? Don't let me do it wrong.
You chose 5 because
Yes. Yeah, you can expand that out and it should do sines and cosines and it should work. Then, are there, but notice this, I could write it as e to the I pi, but I could also not just stop at pi, I could go around another 2 pi, couldn't I? And I'd land right back there again. And I could go another 2 pi and I'd land right back there again. And I could even take another trip around the circle of 2 pi and right back there, and every time it's -1. So what you say is, s squared being -1, it's not just 1 ei pi, it's ei pi plus 2 times k times pi, comma, k is equal to 1, 2, 3, dot. Just extra trips